I'm not going to talk about the JUnit, but I will talk about important testing theory. You're testing the software looking for bugs. The first bug, in case you know what is a bug, this was actually a bug. Well, a moth actually, 1947. A very smart woman who was a prof and a Commodore, Rear Admiral lower half, she actually found this. In the device, it was the Harvard Mark II, where it was a mechanical machine, physical moving parts that did computations, and it was producing wrong results. And they looked through the physical mechanism and they found an insect in there. And they took the insect out, it worked. And that's the term, the bug and debugging the program. Quick history. Importance of testing. Some metrics on why. I could have found some, but Professor Hudson had some. So I just used his, but I credited the source. It's polite, but it's also the academic misconduct thing. I'm using someone else's stuff, I cite it. So I pretty much copy pasted it. You may have seen some profs that have said, you should not, something to the effect of, there should be no bugs in your software. You should be ashamed if you have any bugs. In real life, that's not the case. You should aim for few bugs, but in anything but something that's, say, just a little bit bigger in Hello World, there will be bugs because it's just too bloody complicated a system. The bigger the program, the more bugs there are. And this is pretty much what I've heard as well, too. Although it kind of hurts and you may feel inadequate when you find bugs, it's actually a good thing. Everybody has bugs in their system, even experienced people. And just not trying to find bugs because it makes you feel bad and inadequate is not a good thing. More on the importance of testing, actual real life examples, if you're not convinced, testing and debugging software. Myself, quick story is, I obviously know how to use technology reasonably well. But when I buy stuff, I'm skeptical of having too much technology. Having those extra features are useful. I'm at home now, my smart thermostat programmable features are useful. But the thing is, if the software interferes with the basic turning on and off of the system, that's where I start getting really hesitant. An example of a bug, and to be fair, it was actually tied into hardware problems, software updates, because it's basically like a mini computing device. It has to update the software. In one of the updates, it updated, and then the furnace shut off. And then the thermostat itself wouldn't turn back on. I had to basically reboot both. And I had called in the furnace company and installed it. And the tech, before looking at it, he kind of talked down to you. And he said, well, you have to wait for a while for it to update. I said, 3 hours? And he said, no, not that long. So he figured, I'm computer literate, just know how to use it. Another example, more extensive. I had to buy a new car, so I'm not boasting here. I was required to buy, well, if I wanted a car, because I didn't have anything at the time. And this car when I was shopping for cars, the salesperson first was selling me on technology. The entire phone to it has these features. And I basically was hesitant. I said something effective, I don't want to tie my phone to it. And then his shadow went through his face and he thought, uh-oh, this is like some old grandpa that doesn't use software. And he says, well, and he started kind of talking down to me, saying, well, I had this little old lady who she just turned off all these features. He thought he didn't know how to use it. And she just used the speedometer and that's it. It's not that I'm hesitant in using it, but software has bugs, and if these bugs interfere or make it unsafe for driving, that's where I'm hesitant. And the quick example I had was, this isn't the dashboard, but this is the control panel for extra things like the stereo, things like phone, what else? It also has this particular make and model where you can call for help because they have apparently some help system and they have tow truck drivers or I don't know, roadside assistance. One time I was using it, the touchscreen froze. I couldn't get it back. And I thought, uh-oh, I hope that that the dashboard was still working, but I hope that they're independent. But to be safe, I had to basically reboot the whole thing. Not sufficient. This is an example of technology here. And no, it wasn't infected because actually I don't connect it 24/7 to Wi-Fi because it can be infected. Security isn't necessarily a high priority of these smart devices. And if it gets onto one device on my network, home network, then it can start attacking other devices. So this should convince you the need for testing. So these are people that should test essentially. That's where I left off. Both the programmers, but ideally get people who have no stake in in writing the program. What's involved essentially? It can involve syntax errors isn't the issue. I mean, the programmer should be getting the syntax errors, fixing those ones, finding those ones. But runtime errors, things that are going to crash the program, and then basically looking for logic errors. The correctness of the program is essentially doing what it's supposed to be doing. If there's a logic error, then it's not doing what it's supposed to be doing. That term correctness you'll see in some of the higher level computer science theory classes to prove the correctness of a program, prove that it does what it's supposed to be doing. So you're looking at finding these problems. You're finding these bugs, and although you might find bugs, although you've found some bugs in a program, it doesn't prove that your program is bug-free. That's not the same thing. Why? Suppose I'm working on a program and I found 50 bugs and fixed them. Does that mean that there's no bugs anymore in the program? Not at all. Because with the metrics I showed with the testing part of it, Professor Hudson's, that in all programs, unless they're trivial ones, there's going to be bugs. You found 50, but there could be other bugs beyond, and they're almost certainly beyond those 50. So the bugs you found prove that there's bugs, but there's the bugs that you haven't found. And just the debugging process doesn't prove that there's no bugs. Now, techniques for finding bugs. This is what I didn't get to in this class. They're actually quite valuable. Some of them other programmers do, but I've more formalized this because it is such a valuable technique. There are formal debuggers in IntelliJ. I told in class that anyone use the IntelliJ debugger. How did you find it? I haven't had time to try it myself because I've just been swamped. One student stuck up his hand and he said he tried it and he said it's pretty good. You can set up things like breakpoints and other things, see the contents of variables. It's pretty easy to use according to his opinion and is a student. So I'll take it as a given that the average student can use it. So it's good. You're covered for this class, I hope. But sometimes there's programming languages, it's not uncommon, where there's no debugger. Then how do you debug a program? Fill out some fancy debugger. It helps handhold you. For instance, if you're programming in assembly, required course CPSC 355, there's no debugger typically because you're programming so low level. Even in higher level languages like C, when we were writing programs, and C++, there was no debugger, so we developed these techniques. Now, Professor Hudson's core notes, he kind of briefly talks about this, where he says you can have debugging messages that trace the execution of the program. That's all he says is a sentence or a bullet point or two. But I wanted to expand on it because there's much, much more. I wanted to talk about some of the things that other programmers have done. So what can they do? Debugging messages. This is very handy. One example here, you have a logic error. The logic error is typically caused by a variable that's set incorrectly. And it can be a very complex program where there's many calculations or many changes of variables, not just calculations. It could be a string. It could be some object that's set wrong, and you don't know which one. Well, ideally, what you should be doing is testing and debugging a piece at a time so you don't have to go through the whole thing. But if you've screwed up, or if you find an error later, then what you'll have to do is essentially display the state of the program, different variables to be able to figure out, okay, based on this part of the program, this variable is supposed to be set to this. Let's see if it is, confirm it. Because your formula could be correct, but it's your variable somewhere set wrong. And you think, well, that's really strange. But think in terms of just the scanner class. You read things wrong, a string, for instance. Remember that? It reads the end of line marker. It can completely throw off your program. File input and output, you're reading it wrong. You missed the first line, you missed the last line. Double check that what you read in is correct. That's why a lot of the file input output programs echo back line by line what you read, which we'll get to after reading week. So just having something like this is handy. Now, on that note, if you are asking, say, one of us for help, on that note, TA, I double check with this. Remember, I pushed to have CT, specific Q&A help sessions for this semester and expand them beyond what you had in 231. 231, they basically just converted the last tutorial before assignment due date. They made them open Q&A ones, but I convinced to include some. And they agreed, or myself for help. especially me, this is what I require. Maybe the TAs are willing to try something different, but I find it works better this way. Send me your program in editable, executable form. So basically your class files, include them as file attachments. Don't copy paste them. Don't make a screen grab of it, because I will, if it's just a screen grab, I'll take a quick look and see if I can figure it out. But if it's anything other than a trivial one, especially in the case where people say it's in this part of the program, it probably isn't. It's in another part that you're not showing me. If I can't quickly figure it out, I'm very pragmatic, so I'll try and speed things up. I'll put little debugging messages in order to figure out where the pinpoint, give me clues where the error is. Now, this is why I need an executable program that I can edit. Someone asked me in the end of class, for instance, can I screen share with me? And then I can see their code. Even if it was just my office time, I don't like to do that myself because I like to put in these manual debugging messages. And yeah, I can tell the other person to do it. Say, go to this one, type this here. No, wait, you screwed up. Go over here, type. It's very slow and cumbersome relaying those orders, essentially. If I have it, then you can screen share on my machine, you can do it. Some TAs aren't as experienced as me, don't realize how awkward this is. But anyhow, I asked for the code for that reason, the complete code. And that's basically what I said to the person at the asked me at the end of the class. Send me the complete code so I can do things like this. And quite often, I have seen this, and I've done this myself with a student, and more rarely as a prof, where the logic for my program is correct, but for some reason, say I've read this in wrong from the user. It's like that scanner problem, or I've read it in wrong from file, or I'm grabbing an array element the wrong one. Don't assume that this is correct, because all this could be correct, and it's this one set wrong. That's a simple debugging message. There's more. The term I have, this is basically what Professor Hudson refers to. He only says one thing about this in a point or two. Basically, a trail tracing messages. And it shows how execution unfolds. He says something to this effect. My term is laying out trail breadcrumbs, which is very, very useful. Sometimes actual students have had this. They say, this bloody function or method, I've stared at it so many times, I've hand traced it, and I'm sure it's correct. And some of them might have even done what I did here, and they have these debugging messages to check the values of the variables inside the function. But the thing is, what they have done wrong, I found, is they either didn't call the function, not if they have debug messages, or they called it in the wrong order, or in the wrong time, or a wrong number of times. So having these little trail breadcrumbs can be handy to see, okay, this basically shows the name of the method, and I put this other stuff so I can tell it's debugging messages. That's my own convention. And checking that trail breadcrumbs to see, okay, here's the method called a trail. And when a program crashes, you see the runtime errors, they actually do the equivalent of that to help you debug it. They say in Java, and they start going through the Java classes line, and then eventually, it's either top or bottom, I forget which, they have the line in your Java class. So the trail breadcrumbs is exactly what they have with the Java runtime errors. Another time it can be, this is actually more handy than it seems. Keep this in mind, having these debugging statements. And if they get kind of ugly, what you can do is set up a flag so you have a variable. And this is where you might have a class variable. Say you have class debug, and then you have a flag, could be global. And you have a debugging mode. Only if the debugging mode is true do we display these messages so we don't mess it up. I didn't think of doing this in the morning's class, but if you find, you can actually keep these in production code and then basically toggle debug on and off at different points of the program. We want to turn debugging on and off. Another time for future use where this can be handy is probably not for this class because it's very hard to do this. You gotta be really bad or really good to do this. But languages that have pointers, when you can do things like have a pointer, not a reference, but a pointer, and actually put an integer in there. It doesn't strongly check type that way. You have to do some casting, but nonetheless, you can have a pointer point to whatever numeric address. And it's not so obviously done like that. Sometimes you might trash a pointer within array bounds. You're gone beyond the bounds. Anyhow, it's so tough, apparently so tough to trace it. I remember a debate in the department meeting. One prof stood up in the department meeting. We're moving away from C, her argument, to go to Pascal. And she said, well, Do you want to keep C? She said, no, that prof, and that prof was a graphics person, found C useful. And he said, well, are you willing to help the students debug their pointer problems? The implication was it's so hard debugging it. It's not necessarily, I found, because I was such a lousy coder as a student, I had those pointer problems that would crash my program. It's easy to do with C. But I set out my trail of breadcrumbs, and it somewhere along the line unexpectedly crashed. So I basically had all these print messages, and I just followed the line of print messages, and where they stopped pointed clues as to somewhere after here is where I've screwed up that pointer. So that's something to keep in mind when you take a language that uses C or C++. Very, very useful. And as an undergrad TA, I was actually in that help tutorial, CT, helping students. And this is, if I didn't have time to type in these messages, I frequently had so many people, I would tell the student specifically, put these messages, I'd do this, and this, tell them to type and go off and do it on their own, then I could help another person. And it really did help students. So it's not necessarily as hard as even some of my colleagues are kind of afraid of that. And that's one reason, among others, why we switched from C, because they thought it'd be so hard to deal with these pointer problems. But these breadcrumbs aren't just limited to method calls or pointer problems. This is another invaluable tool. If you have your program apparently hanging, you run it, and it just basically, you say, this is what beginners might do. Say your program's running and it's not back at the command line, it's just sitting there. My program's not working. There's a few things to do. If I hit enter, that's one thing. It's waiting for user input, but they forgot to put a prompt. So they forgot a print or print a line to say enter something. It's got like a scanner, it's getting information. And I hit enter, I've told the program user input, I'm done, and then it proceeds with the rest of the program. The other thing that might be causing that is basically an endless loop. And they can't tell which is the endless loop. Now, this seems obvious after I tell you, but there's students, many students that don't think of doing this till I show them, putting these different printlns and basically trying to see which of these ones, message 1, 2, 3, or whatever, is appearing. And that tells you which is the endless loop or loops. If we see a 2 up here, then that one's the endless loop, for instance. Simple to do, very easy to find those endless loops. Or with branches, they say, okay, they have some complex branch. They say, it's not working here. But what they didn't do was basically try and test each branch. And somewhere in here, they've screwed up. Part of it could be that there are many reasons why. One is their variables are set wrong, so their conditions aren't right. Or their conditions, Booleans, are wrong. Another thing, these things might be leading to the branches not executing when they should. So what you could do is you can display the values of the branch controls to make sure it's set to the state. Okay, I expect this one to execute. If I do expect this one and this one, given the variables, do I see these messages? If I don't, then that pinpoints that there's logic errors in my relational expressions, my Boolean expressions there. Another useful one. It doesn't replace hand tracing, but what it does is things like this can help you pinpoint where the problem is in a big program, and then from there you hand trace and you just pick apart under a microscope the part where it's suggesting the error is. Now again, some of you have taken 231 when it wasn't a coordinated version, spring, you told me, and I've actually had the TA specifically go through this. This is a quick synopsis of it. Because you're more experienced in 231, the synopsis is probably enough. But if you're still unsure of what I'm talking about, ask. And in this case, because this is my technique specifically, don't ask in Discord because they won't necessarily know the notes. You might be able to ask a TA, but if you have to show these examples so you can figure out the context. Or me, I'm the most likely person to be able to tell you how these ones work. Breakpoints. Has anyone used the debugger in IntelliJ yet? Hands? And if you've used it, try the debugger out. Okay, second question. Does anyone know? Oh, well, here's the term, actually. I was about to say, anyone know what it means? A breakpoint is basically where you're pausing the program. It stops at a point. And there's some reasons why. The person who said to use debugger maybe it was an experienced programmer or he found it really useful. The one in IntelliJ, he said, I can stop and I can look at the contents of variables. That's one case where you'll use those breakpoints. Because if you have a lot going on calculations, step through is where the intermediate, if you have a big calculation here and it consists of intermediate ones, check out with the breakpoints, what is the result of the calculations here? And then next part, pause, what's it here? That's one case where you can set up a breakpoint. And with the debugger, he apparently said it's very easy to set it with the IntelliJ, not all debuggers, it's easy to do it. Another case is endless loops. If you get multiple of these messages, for instance, or too many, one and then two, trying to figure it out, you can pause it part way through. Say, pause it here. That's the idea of breakpoint. And then that'll help you maybe put in some debugging messages, the state of the, oops, this is no loop, the state of the variable, that's the loop control here, for instance. Now, with the breakpoints, you can actually manually set these up where the program pauses at points. How do you do it? Well, with text input, when it sees that in, and it's waiting for text input to put it in a simple-minded form. How does it know the text input is done? This is looking for a string, but if I just type in a string here, it doesn't know the string is done or the number until I hit enter. So what you can do is set this up so it's waiting for user input. You're not going to store the input because you're just giving the person a chance to read the debugging messages or whatever you have and just say press enter to continue. Dead simple way of saying up a breakpoint. But well, it's not logically hard, but you have to type in all this text and import scanner. A little bit of work there. But it can be also very useful. The debuggers now, they're tools specifically to help you debug a program. They're often built into IDEs. Some of them are very easy. Some of them, in my opinion, aren't worth the time. I do manual techniques. Another reason for manual. Unless I was using that language for long-term, then it might be a long-term investment to invest the time and jump through the hoops and figure it out. But properly implemented, debuggers can actually allow you to do some of the things that I'm talking about, like the breakpoints. Great. Where's my... where's my mouse? Oh, here it is. Here's on another screen or something. I don't know. Okay, breakpoints. This isn't logically hard to do, but you have to type in a lot of stuff. They can do it easier in a debugger if it's available. For instance, in my opinion, I've programmed in a lot of languages, and the easiest debugger that I've encountered so far is the one that's built in with Microsoft's programming language. This is for C# Visual Basic for applications. I actually teach a VBA course. And this is programming in Microsoft Office. I taught them how to program, actually augment Word and augment Excel. Anyhow, this debugger, if we want to set up a breakpoint, here's the code. And you can see it kind of looks a little bit like similar language that you've seen in Java. And we click in the margin, and that's where breakpoint's set up. And we click to toggle it on and off. It's that easy. So it's easier than the approach I saw with Java. Python's a little bit easier setting up breakpoints, but still more work than this. Another thing you can do is, the student in this morning class said you can set up breakpoints really easily, and you can also see the contents of variables. In this one, there's two ways of doing it. I don't know if you can do it in IntelliJ or not. I can mouse over variables like this, and it'll have a little yellow pop-up telling me what's the contents at different points in the program, or right here when it's here. And it also has down here a window, so I can say view, forgot variables or something, and it shows me all the variables. And I have a breakpoint telling me at the arrow I stopped here. So I haven't initialized them yet. So they're all set to 0 by default. Makes sense. Then when I get user input, the first number is 888, second number is 888, 666. Now I hit the second breakpoint after I've entered that user input, and see 888, 666. Very handy. And it automatically shows me, presumably these are just local variables, because I have a big program, it's going to have way too many variables. But this gives you an idea of debugging techniques and some of the things that you can get. This testimonial from this morning student said he said you can do these things very easily. So I recommend, if you have time before A1, try it out. You're probably pressed to get this done with A1, even though you got till Tuesday. Try it over reading week with some simple little programs, get familiar. It'll be apparently not hard. It won't take you long, but it could be worth a lot. And the other part, the manual debugging, Potentially, if you find some of the features don't exist in the IntelliJ debugger or they're hard to use, then you can go back to manually doing it. And the manual is useful for the future. Okay, let's go on here. Assertions. Now, in tutorial, by this point, it's Friday, they would have shown you how to set up, oops, I'm not going to go in that screens mode, how to write your tests are assertions. The assertions aren't all that hard, essentially. Typically, what they are is they're logically equivalent to a branch. And if the branch evaluates it true, then it's going to produce a runtime error, which sounds really strange. Why would you want something to crash the program? But the idea is you're testing the logic of your program. And if you recall from last semester, the profs had taught you that it's easier to figure out a runtime error because it stops the program at the point where the runtime error is occurring, tells you the line, and may give you a description, as opposed to a logic error, which invisibly occurs. Now, assertions, however, aren't tied in specifically to JUnit. You can actually use assertions without the JUnit testing kit. Sure. If you're having trouble with JUnit or you want to quickly write an expression for an assertion, you can do it within Java. And I think the syntax is either identical or similar to in C and C++. You don't have to import anything. So here's a segment of a program. I include it in a class called assertion test. This is the key part. So age, it's basically saying it's asserting, is it true that the person is an adult? If it's not true, then it's going to have this runtime error saying not adult. The person's an adult according to this, and then it echoes back the age. But if the person enters in an age that is not an adult, runtime error, and then we get this error message. And it tells us the line number, which is this one. It's better if we require the person's adult to proceed, better to crash it and try and fix the problem here. Now, to use assertions in Java, these are debugging messages. So by default, if I ran this Java assert test, this wouldn't be running. You have to add the command line argument, essentially, EA minus EA, presumably enable assertion. That's what I think it stands for. So in real life, you can actually, they do this. Real programmers put these assertions in the code. The user doesn't see them. And the only way that we can see these debugging messages is when we go in debugging mode, and users won't know to do this. So you actually do have assertions in C, Java, C++ code in real life. But in so this is if you want to create some expressions and you find it's too much work to get done with JUnit. It doesn't provide the functionality, but quickly allows you to put some various expressions. But for this class to be clear, you have to use JUnit, which is covered in tutorial. And Professor Hudson, I quickly showed in week 4, put up a new video. Debugging process. It helps you find bugs and then find and fix errors. Now, he has terminology here. I don't necessarily, the ones in brackets, that's why I put them in quotes, agree with this description of them, but this is how he described it, so you might have to know essentially these terms in a quiz. So over here. But the key part that I fully agree with is coding is an iterative process. You keep going back, it's cyclical fashion. So you test, you debug, try and find the bugs, fix the bugs. Oops, my arrows are kind of funny. Oh, there's a bug here. It should be actually going, I used the wrong arrow. Should be going back up here. You know, it's that bug in my bug notes. As you debug, you test again, find. So you spend as much time going through the cycle as you can invest in that part of the project. This is opposed to something you may learn a traditional technique. You may learn this in the second year course, software engineering, or SENS 300 or 301, I forget the number, where you learn software development techniques. The traditional technique is called the waterfall technique, water and fall. That's the actual term. The idea is the waterfall is you have steps of the software development process. And once you go from one step, it's like a waterfall. You get the next step, you can't go back. It's not iterative. So for instance, you have test and debugging. Then after you finish that, you're not supposed to go back. And that's not done anymore, but that was a traditional approach. You're supposed to test and debug continually. Even if you've say gone and showed this to the user, for acceptance, you find bugs, of course you should go back and test and debug. That's a part I fully agree with over here, that it feeds back upon itself. Categories of tests, black box and white box. Now with these ones, it's theory, but it's theory that's applicable. And after I found out last weekend, just before a week ago with Professor Hudson, he said, okay, with tutorials, I told him I don't have time to cover the JUnit. He said, fine, no TAs will do it. Then I focused on stuff like this to try and expand upon, to make it clear, to have concrete examples. So I had time in lecture. I won't spend too much time. Black box testing. Basically, the idea of black box testing is all your job is, if you're a black box tester, is you have various inputs. Say you're testing this function or method that produces an absolute number, various inputs, and you're comparing, given these inputs, is the output correct? So if an absolute number, if it's negative, it's supposed to produce the absolute value of it. It's supposed to return positive. Positive numbers stay positive. A zero is neither positive nor negative, zero. That's the idea of black box testing. It's a black box because the actual code of the function you don't look at, and you have no idea the implementation. You don't care as a black box tester. All you're testing is the correctness in terms of inputs and outputs, which is important, very important, the bottom line, but it's not the only part of testing. Now, with black box testing, just like I said before of testing, you won't be able to test all possibilities. And I used a simple little example. If we have a branch or loop, and the loop control is a integer, 32 bits, 32-bit values, that's 4 billion values. You're not going to test all 4 billion values to make it correct, make sure it's correct. For instance, if we're checking to see if age is greater than or equal to 18, there's no need to test ones 4 billion, 4 billion 1, 4 billion 2. What we're trying to test in that case is probably the boundaries around 18. So what we develop, essentially, those boundaries are what we call the boundaries group equivalence classes or equivalence partitions. Example, right here, the equivalent classes, there's one. Negative numbers, because if it works for one negative number, it works for another negative number. Another equivalent class is the positive numbers. So we don't test for, theoretically, every positive number from greater than 0, even integers, 0 up to positive infinity. By definition of infinity, we would never finish the test. But we test at least one value from that equivalence class. Now, this one is pretty much a given. There's not so much the boundaries, but something that has a boundary, so it tends to be binary. It either is or isn't negative. If, say, we had a pass-fail course, percentages, and we have a few, even with computer science. When I was at work on calendar entries, I actually shepherded a calendar entry for a new faculty of science course, 300 level. Pass-fail only. So, pass-fail, we could set that pass rate, whatever. It's 50% typically, but some courses are higher. Nursing clinical courses, I think it's 75%. But I say 50%. So if we get 0 to less than, see how I've drawn this diagram, then that's the equivalence class here. That's one category. Another category includes the values 50 and greater up to and including 100. But the other ones include the error cases, less than 100, but not 100. Greater than 100, but not 100. So what we should be testing for equivalence classes is bare minimum 1. But that's the absolute bare minimum. The real bare minimum is at least testing just below boundary, for each boundary, test just below, right at the boundary, because if people screw up, it won't be in one of these midline values, it'll be at the boundary. Does it include? Does it exclude? Should it include or exclude? And then one right just on the other side of the boundary. And we do it for all 3 of these. So with 3 boundaries, we test the real minimum 9 cases. This is theory again, but important theory because these techniques are applied in real life. Plus, if I were making up a midterm or quizzes, these are possible theory questions that I would test on. Don't know if Professor Hudson would test on them. It's very much fair. I don't know if he did test on, but he could. And I'd agree that it's something that is fully fair game. Just to add in, Black box testing isn't limited to just numeric cases. So this is where I take the time to do this. No number calculations here, but if say we're black box testing the code to make sure, say the office, the ribbon, when we click on one of these tabs, the home tab, it's the currently selected one. If I click over here, slideshow, that will be the currently selected tab. Black box testing, the equivalent cases essentially, clicking on the tabs and possible equivalence partitions, click on the tab that's already selected, nothing changes. We shouldn't go to another tab. Another one, click one or more times. So the equivalence class is the one or more clicks within that feature. And it's not just numeric, but essentially it's cases non-numeric that where we can do black box testing too. White box testing is another form of testing. You'd likely do the white box testing before the black box testing. This is where you actually not only see the code, but you're evaluating all the details of that block of code. Notice I don't have the whole program, but one function or method. So what do you design with white box testing? The details are all visible. That's the white. You shine a light on it. One is the idea is you're covering all instructions. Coverage testing. The coverage means you're ensuring that all these instructions execute, which isn't necessarily the case. Under certain situations, not all instructions execute. Now, Java, the compiler, actually checks for these cases and flags it as a syntax error, but not all languages will do this. So you might have, for instance, a variable. It could be a string, not just numbers. You don't initialize it. And then we have various Boolean expressions. And then say within this body, S is set to some value. However, we have something else here, an else. We don't have an assignment statement for S. The Java compiler will detect that because it's in the body of a branch. It doesn't always get executed, but there's possible cases where not all statements get executed. So ensuring all statements get executed at one point, given that this Boolean expression is false, for instance. All paths of execution are tested. This isn't the same as testing all cases. So if I had, for instance, paths of execution would check to see, does this body actually execute? Does this one? We test all branches, or if this was an if-else if too. We check this Boolean expression. That's a path. I don't know, someone's near immortal here for the 1,000. This isn't the same as testing all values, because all values, this is the path, this is the path. All values would go through all 4 billion odd cases of age, which is not what we do. Now the JUnit testing, it's covered in tutorial. The main now becomes whale. I showed you quickly under week 4, there's a new video Professor Hudson put up. He said that he actually shows you how to configure, at least within JUnit, how you can, when you do the import, if you don't configure it, it's going to say, I don't know what the Jupyter JUnit org is. The configuring basically configures the class path, so it knows where it's installed on your device. The other thing I suggest is you have to do this sometime during the semester, Professor Hudson said, only for a little part of the course. You have to be able to compile programs here at the command line, compile and run. Now, what you might want to do after the assignment 1 is due is install the Oracle Java and then figure out how to configure your computer so that this works. If it doesn't, if you haven't configured, the first part is configure the path. Oops, Java. Oh, Java. Because if I haven't configured it, right now I'm in this directory, week 5 command line. I type Javac, it doesn't know where to find Javac. But when I typed Javac, the Java compiler, it said I used it wrong. It told me how to use it. So it knows where Java is installed on my computer. The first thing you have to do is configure the path to where Java is installed, where programs installed. The second thing you have to do is set the class path if you have an extra library that's not part of Oracle's, such as JUnit. essentially the class path, wherever I have put the classes that I use for JUnit, I have to basically set the class path in Windows. It's called the environment variable to point to where JUnit's installed. So what I suggest is, over when you get some time between assignments, perhaps reading week, try and figure out how to set up, download and install Java Development Kit on your device if you have one, or at least try and use it in the lab if you don't have a device, which is perfectly possible too. And then try and figure out how to, with say JUnit, if you have time, how to set up the class path so they can access JUnit. The ports won't be sufficient.